Right. Yeah, I'm working with DStack, where we built an open source framework for running GPU workloads and all kind of Gen AI workloads as well, including LLMs. And today I'll be talking about open source LLMs and how to tweak them for production. This is going to be a pretty introductory level. So if you are an expert in LLMs, probably you'll not learn much, but still we'll see. But if you are a beginner or intermediate level and basically curious about what are these important questions around using LLMs in production, that might be a great fit. Let's see how it goes. Right. First question, which we're going to talk about today, is why using open source LLMs anyway? Well, we all know about ChatGPT and proprietary LLMs, and I bet that most of you actually had some experience with this. I also put a small poll, which you can find on the right-hand side, and vote what level of experience you have with open source LLMs. So we're gonna see in the end of their presentation. But for now, let's start with a question of why to use open source LLMs, given that there are proprietary models. So there are 4 fundamental reasons. First reason is control, and this is something that people talk a lot today. When you're using a proprietary model, you don't have much control of the behavior of the model, and if the model behavior changes from a release to release, your business might be at risk and your application might stop working. There is also risk of that particular provider might change something, how they offer that model. And of course, open source LLMs have a lot more control. Basically, if you own the weights of your model, you can decide how they are served and how exactly they are integrated into your apps. So it starts with owning your weights, and this is why open source LLMs is a big thing, because weights are, well, not yours, but they almost yours. They are open, and you can use them without any restrictions. Then customization is a big thing, and this is why there are very popular models, which we'll talk about in the further slides. Open weights LLMs are great because you can build on top of them. If a company releases open weights of the model, other company can build on top of this and reuse the approach that LLM used, or use a custom data set and tailor their model for a specific use case. So basically, it's all about community, and you can very easily build on top of open source LLMs. Then there are 2 other factors. One is cost, which is a difficult topic to talk because there are so many dimensions, but there are certainly cases when you can significantly reduce costs of using LLMs if you are using open source LLMs. This is typically done by using a smaller model, also leveraging batch inference, and also increasing the quality of the model by leveraging fine-tuning and all sorts of customizations. And finally, of course, privacy is a big topic. And again, this is a separate thing to talk about. Every company has different expectations in terms of the privacy, and to a certain extent, there is no problem with using OpenAI and similar services when it comes to privacy. But of course, when you are using open source LLMs, you have entire control. You decide how data is processed, and you can be sure that there is no privacy issue there. Right. The next slide is about major open source LLMs, and by no chance I aim to talk about all their major releases of LLMs. It's just not physically possible to mention all of them within this talk, but I would just mention several which probably you're already aware of, and those that you really have to know. First is, of course, Llama 2. Llama 2 is a model by Meta, which is offered in partnership with Microsoft. And this is probably the most popular open source model. And it is offered in 3 different sizes: 7B, 13 billion parameters, and 70 billion parameters. This means how large is the model, how many parameters are in the model. But you can think of this as the size of the model. And the larger the model, the better the quality is. Then it's worth to mention that Llama is offered not just in 3 different sizes, but also in 2 different flavors, let's say. First one is a base model, means that this model can complete text, generate text, and there's also a version that is fine-tuned for following instructions or having conversations, also known as chat model. So Llama is offered into these formats. Then, and well, to mention about Llama 2, this was their in terms of quality, one of the best models, and it comes with a license that allows to use this model commercially. So this is why there was so much buzz about Llama. The model is really great. It's very customizable, and it can be used commercially without restrictions, or almost without restrictions. Another model to mention is CodeLlama. This is basically another model by Meta, which is a fine-tuned version of Llama, but it was fine-tuned for generating code, which is a big thing and a totally separate use case, very important for us. Why? Mainly, well, when you're working with LLM, it can generate human readable content. But if you are using something like CodeLlama, it can generate code. And then it means that you can automate the execution of that code. For example, think of 2 use cases. One use case is you can generate SQL code and automate the access to your data on behalf of the model, which is a very powerful use case. Another one is generating, for example, JSON. And JSON means that you can generate API calls, means that you can automate accessing third-party services on behalf of the LLM, which is a entirely different level of automation. CodeLlama can not only complete code, it can also change the code in the middle, the technique known as fill in the middle. And it's also offered in 3 different sizes, though the largest model is not 70 billion, but half of the size. And the third one in our list is Mistral. Mistral is a relatively new model. It is released by the Mistral AI company. And what is great about Mistral is that it's one of the most capable, smallest model. So it's only offered in the 7 billion parameter size, but it outperforms all of the model of the same size, and even some of the model of their larger size, like 13 billion parameters. Here's a slide with some benchmark data. It is from the original paper of Llama 2, where it compares Llama 2 to some other models. And what we see here on the left-hand side is the list of different benchmarks. Benchmark is basically something that measures how a model behaves in terms of quality on a specific task. First one is MMOU, Massive Multi-Language Understanding, just simply tells how good the model overall across different tasks. And what is worth mentioning here is that Llama 2 comes really close in terms of quality to GPT 3.5, which you might be familiar with. And at the same time, you can also see that Llama 2 falls behind significantly GPT-4 behind GPT-4. So basically, it's almost good as GPT 3.5, but it's not as good as GPT-4, like significantly, which is no surprise because Llama 2 is 70 billion parameters, while GPT 3.5 is 135 billion parameters, like more than twice bigger. And GPT-4 is 10 times bigger than GPT 3.5, which is amazing difference, but still you see that open source LLM can come really close in terms of the quality to proprietary LLMs. Right. Here's another benchmark data now about Mistral. Basically what this benchmark data shows is that Mistral across various benchmarks beats models of the same size, and it also beats quite a few models of their twice bigger size, which is just another way to say that Mistral is a super efficient small model, and no surprise why Mistral is used when it comes to working with small models. Mistral is also very customizable, and it beats Llama in quality when it comes to the size of small models. Right. Here's an example. Here's some data from Snowflake, where they took Llama 2 of different sizes, and then they fine-tuned this model for a very specific problem. In this case, generating SQL queries. And what they learned is that just by fine-tuning even a very small model, you can achieve a quality of, let's say, the largest one, or even come really close to GPT-4. So here you see that the fine-tuned version of Llama 2, 7 billion parameters, came almost to the same accuracy as Code Llama, 34 billion parameters, and not that much far from GPT-4. This is another benchmark data showing now Wizard Coder and Find models, which are fine-tuned version of Llama, where they basically aimed at beating GPT-4 when it comes to code generation. There's a funny story about how this went out. Basically, GPT-4 back then, when they worked on this model, was not that good on code generation, and they basically proved that it is possible to fine-tune Llama 2 to be much better than GPT-4. Well, what happened in the following weeks that OpenAI basically updated their model, and as you see here on the slide, GPT-4 is still the best when it comes to code generation. But also to mention that it is possible to fine-tune Llama, or if there will be other open source models to match the quality of GPT-4 for code generation. So let's talk about some economics on like cost. And here's a screenshot of an app which you can also find on Hugging Face Spaces, which if you give it a name of a model, it automatically calculates how much memory you would need in order to run inference or training with that model. So here, if we take the largest Llama 2 model, 70 billion parameter, then you'll see if we take the original, their full precision, basically if we take the weights in the full precision, you know that weights are float point numbers, and the full precision is what is this float point 32. You would need 256 gigabytes of memory just in order to run inference with that model, which means that it's not even possible to fit this model into one single GPU. And this is a big problem. Now, if you look at training using, for example, the standard Adam algorithm, then it's not possible to fit into a GPU. By no means. It would need 1 terabyte of data. But in the further slides, we'll see what we can do about it to make it easier. Before we do that, here's a slide showing the study by Hugging Face done together with AWS. What they did, they took 3 different sizes of Llama 2, and then they tried to run inference there, and then they measured latency and cost per token and per million of tokens. And what you can see here, for example, the last row, if you take Llama to 70 billion parameters, you would actually need the largest AWS instance that they can offer, one that the most expensive one that has 8 GPUs of A100, each 100 gigabytes. And then for one request, for one token, you would need 41 milliseconds, and with just one concurrent request, which is just a way to say that it's not really fast in terms of the latency. And here on the right hand side, if you look at the cost, you'll see that basically in order to generate 1 million of tokens, which is, well, not that much, but you would need basically $427, which is a way to say that it's pretty expensive and pretty difficult to run inference with an with any model, but even with open source model. So now we'll talk about some very basic techniques that allow us to reduce the requirements and make it easier to use LLMs. First one is quantization. So if you know, as you know, an LLM is basically a set of weights, which are just float point numbers, and most common way to represent them is through float point 16, and it's called also as half precision. And even though it's half precision, it's still a lot of memory needed in order for inference and for training. So that's why there is such a technique called quantization. And it works the following way. You convert the weights from the float point 16 format into, for example, int 8 or int 4 format, which is just another way to say that you lower the rank, lower the precision, and change the way these weights are represented. But by doing this, the best thing about this is that you can do this with very little drop in quality. And this is a very big thing, because now by lowering the precision, you improve the latency, basically the time, you reduce the time needed for inference and for training. You reduce the amount of energy needed for that. So it is very helpful in many ways. So now if we look at the same memory calculator, where we see that if we reduce the rank, we also reduce linearly the memory required for inference and for training. For example, if you are using the largest Llama model, and if you, for example, take int 8 precision, then it will be 64 gigabytes only for inference, means that you now can fit it into one GPU. And if you don't have that expensive GPU, you can go even lower precision and, for example, use int 4 quantization, and it will fit into 40 gigabytes GPU. Same with training. So by using the quantization technique, you significantly drop the amount of memory required for training, but then it still won't fit into one single GPU, but you'll be able to use multiple GPUs for that, or multiple nodes with multiple GPUs. So this is powerful technique. So now the same slide, but now with quantization used here. So we see that, for example, by leveraging the quantization, we can drop significantly the cost to generate 1 million of token, like almost 10 times, to $60 per 1 million. Right. Another technique, which is very important to know and understand how it works, is called LoRa, which stands for low rank adaptation. The biggest problem with LLMs is that they are very large and they don't fit GPU memory. So this technique allows us to froze the weights of the model and take only a smaller subset of these weights, which we'll call an adapter. And then we'll only load this adapter, much smaller adapter, into the GPU memory, and then we'll use that for training. And then we will train that adapter without the needs to load all the weights into their GPU memory. And then once we've trained that adapter, we'll merge that adapter with the frozen rest of the model to get the final model. This is a powerful technique because it allows you significantly reduce the amount of memory required for training. The best part is that the quality drop is not that significant, and there is a lot of research body of research showing that it's pretty efficient technique. Here's just an example. For example, if you take Falcon, 180 billion parameters, the largest ever open source model that exists, you see how the requirements of memory requirements changes for training. So if you are just using their full precision and without any techniques, it would require from you 5 petabytes of memory, GPU memory, which is just too much. And by using LoRa and then using quantization, you can drop these requirements like an order of magnitude, basically. For example, if you combine quantization and LoRa, it will be 160 gigabytes, which makes it very efficient if you decide to fine-tune such a model. Here's a study that proves that. This one is published by Anyscale. They basically took Llama, 3 different sizes, and they fine-tuned this model on 3 different data set problems. One is for extracting structured data, another code generation, and then finally solving math problems. And what they figured out is that for certain problems, such as extracting unstructured data and code generation, it is possible to use LoRa for fine-tuning to match the quality of the largest model, like the largest model Llama, and also match they come really close to the quality of GPT-4, or in some cases exceed the quality of GPT-4. For example, here, the first one, we basically exceeded the quality of GPT-4 significantly just by fine-tuning a very small version, actually using LoRa here. A few more techniques to mention here before we conclude. If you decide to fine-tune an open source LLMs, it is worth to know these techniques. First one is called supervised fine-tuning. This is the simplest way to fine-tune an LLM. Basically, you take a base model, a model which was trained previously on low quality data. For example, Llama 2 base model is a model which you would take. Then you would fine-tune it by giving it high quality data. For example, if you'd like to fine-tune it to generate SQL queries, you would need to prepare a data set that has a prompt and generated code, and you basically fine-tune your model by using this data set. You don't need to label anything. You just need to prepare answers. Means that you would need some people that would work on this data set. But we'll also mention synthetic data if time allows us. This is the most simple way to fine-tune a model. However, there is even more advanced technique. For example, if you are doing supervised fine-tuning, like here, then you only tell your model what is good. So basically, you give it a data set consisting of many examples, what is good. So this is how you teach the model to provide this good outcome. However, it's not enough if you'd like the model to follow instructions or to be aligned on certain criteria. And this is where reinforcement learning is used, also known as RLHF, where you not only give it what is good, teach it what is good, but also what is bad. Basically, you annotate your data set with labels, like, for example, good or bad, or, for example, a float point number representing, like, from 0 to 10, representing how good or bad that particular piece of data, of prompt and response. And RLHF works the way that you first use this data set to fine-tune an intermediate model, called also known as reward model. So this model learns, like, this scoring, and then finally you take that your model which you trained before, and then fine-tune it using the reward model. So basically there are two stages, and that's how you teach the model to follow instructions, to how to reason at all. So this is one of the most basically powerful technique for teaching an LLM to follow instructions. Finally, there is another technique called DPO, which is much simpler version of RLHF, which doesn't use reinforcement learning. So it works pretty much same way, means that you would prepare a data set and label it, but it can fine-tune your base model without using reinforcement learning. There is a paper on DPO and how it's different from RLHF. So I would recommend everyone to read this paper. This is a very powerful technique. And this is some study by Hugging Face where they show how DPO compares with RLHF in terms of their ease and quality. So basically they took Mistral and fine-tuned it with DPO to prove that it is possible to use DPO to fine-tune even a smaller model to match the quality of a larger model. So they show that DPO is quite powerful. Right. So trying to conclude here, by no chance my talk aimed at talking about all important stuff. There are so much stuff, but there are three topics which I would recommend for everyone to take a look at. One is serving multiple LoRa's. I already told you about what LoRa is, low rank adaptation. And there is a way to use LoRa not only for fine-tuning, but also for serving multiple models and making it possible to fit many models into one GPU. Second is called speculative decoding. This is how you significantly can improve latency. There is also a paper about this, and a lot of studies. And finally, generating synthetic data sets. So one of the bottlenecks when it comes to LLMs is data sets. You need human labor in order to collect data, curate data, and label data. And it is possible to use LLMs to help with that. And there's a lot of things you can do there to reduce basically the amount of human labor needed for creating high quality data sets. Finally, a shameful plug here. As I'm working with this deck, I would just encourage everyone to take a look. This deck is an open source tool that allows you to use any other open source tools like PAFT, TRL, TGI, VLM, and others for training and for deployment. And it also allows you to use all these tools with any cloud. So it's just a very flexible way of running any kind of workloads, from fine-tuning to deployment and dev environments, while using any cloud GPU provider of your choice.